Okay. The title of our lesson today is Clock and Modular Arithmetic, but really what section 2.1 is about is number systems that use bases that aren't like base 10. First, as a review, we're going to do a little review of our base 10 system. Base 10 is the system we use all the time. We have digits in that base 10 system that are 1 through 9, and we also have a 0. So we have 10 different individual digits that we can use. Makes sense? It's a base 10 system. Do notice, though, in any one place value position that we would write down, the largest individual number that we could put in any one of those places would be a 9. It's called the base 10 system. We have 10 different numbers we can put in there, but the largest thing we could put in any position is a 9. We can't put a 10 in there because if we put a 10 in there, well, that doesn't work. That's 2 digits in one place value. That doesn't work. So the largest possible digit we have is 9. And as we go through this, some of it may seem fairly obvious. What's going to happen eventually is we're going to work in systems that aren't base 10 anymore, and we're going to lean back on our knowledge of base 10 to help us understand those other systems. Our base 10 system, we have place values. We have the ones place. We have the tens place. We have the hundreds place. And we have the thousands place. Again, should feel pretty comfortable with that. But let's talk about where these place values come from. Let's see. I have a system with bases and exponents, and you may or may not remember this. Anybody remember anything raised to the 0 power? So if I have 2 raised to the 0 power, or 7 raised to the 0 power, or 15 raised to the 0 power, those all have the same value. Anything raised to the 0 power is, anybody remember? Outstanding. Don't say Emily. Very good. Moylan, excellent. Anything raised to the 0 power is 1. Anything raised to the 0 power is 1. And in order to have our ones place here, that's just 10 raised to the 0 power. We don't really think about that very often. And what will really put that into focus is their tens place is 10 raised to the first power. And the hundreds place is 10 raised to the second power. That would be 10 squared. 10 times 10, that's 100. That's the hundreds place. And 10 raised to the third power, 10 times 10 times 10, that's 1,000. And so the reason that this is called a base 10 system is we can write out the values of the place value positions with base and exponent, base and exponent, base and exponent, base and exponent, and every one of those bases is 10. That's why this is called a base 10 system. Because our base is 10, and when we write it with those exponents, it gives us the values of the place value positions. We'll see this for sure when we talk about other systems that are other than base 10. But that's why it's called a base 10 system, is because the place value positions can be written out using a base of 10 with those exponents that give us the place values. Any questions so far? Great, great. Base 10 system, largest digit is 9, and it's called base 10 because that's the base we use with those exponents to get the values of those place value positions. Something we're going to do with place value is we're going to write a number in what's called expanded form. It's not necessarily the most useful thing in the world, but it helps emphasize place value positions. So that's why it's going to be valuable for us. Here's what expanded form means. If we have the number 527. We could rewrite that. We could, expand that a little and say that it's 500 plus 20 plus 7. Essentially, all we've done there is peel off each of the place values. We get 500 from here, we get 20 from here, and we get 7 ones from here. And then as I say that out loud, essentially what I have here then is, well, that's 5 in the hundreds place, that's 2 in the tens place, and that's 7 in the ones place. If you see anything that doesn't make sense, something that you're not sure of, please don't hesitate to let me know. My guess is that most of this feels pretty, okay, sure, that all makes sense. What's the point? Why would we do it? That's a perfectly reasonable question. And the next step is why we do it. As we look at this then, in expanded form, I have 5 hundreds. And 100 I'm going to write as 10 squared. And then I have 2 times 10 to the first, and I have 7 times 10 to the 0. Because remember, anything to the 0 power is 1. And so the number 527, written in what we're going to call expanded form, is 5 times 10 to the second, plus 2 times 10 to the first, plus 7 times 10 to the 0. The purpose for us here is to emphasize the base 10 system is what we're working on, and those are our place value positions. 10 to the 0 are the ones place. 10 to the first is our tens place. 10 to the second is our hundreds place. This helps us understand place value positions, where they come from, why they are what they are. Here's an interesting question, something you've probably never thought of before, but I'm going to throw your way. How many tens are in 370? I won't do a poll for this, I'm just throwing it out there. How many tens are in 370? Okay, I understand where you're coming from. There is a 7 in the tens place. Instead, let me rephrase my question here. If the number 370 were made up of only tens, how many would it take? So how many tens would it take to get that number? And Courtney's 37 is the right thing there. Yeah, 37. And there's a couple of different ways you could think about this. You could think of this as, well, let's see. 37 times what would give me, what times 10 would give me 370. You could think of it as, okay, how many tens are in there? Well, if I do 370 divided by 10, that'll tell me how many tens are in there. Or you could look at this and say, well, let's see. If I just look at this by examining the tens place, there are 37 of them. Any of those 3 ways is a perfectly reasonable way to get to the fact that there are 37 tens in the number 370. So if the number 370 were made up of only tens, it would take 37 to get there. Y'all that said 7 at the beginning, I totally understand why. I'm hoping what we just did there makes sense. And I phrase that the same way that the book will phrase that question. But I totally understand why, if the number 370 were made up of only tens, how many tens would there be, is a better way to phrase it. So as long as it's clear that way, I think we're good on the concept. Let me try one. How many hundreds are in 31,000? I'm going to set up a poll for this one. How many hundreds are in 31,000? And keep in mind what we're asking for here really then is how many, if the number 31,000 were made up of only hundreds, how many would it take? We'll go another 15 seconds and then talk through this one. Okay, not unanimous, but pretty strong agreement on there on 310. Let's go back and take a look. So as we look at this one, the question is, how many hundreds are in 31,000? So in other words, what times 100 would get me to 31,000? You could also think of this as, okay, if I had 31,000 and I divide that by 100, how many hundreds would be in there? And then the other way to look at this is, well, since we're talking about hundreds, I'm just going to section this off at the hundreds place, and there's 310 hundreds that would be in that number. If we tried it down here, 310 times 100 would give us 31,000. 31,000 divided by 100, there'd be 310 of them. For the other answers that came forward on this one, if it had said how many tens are in 31,000, then we would look from the tens place over. It would be 3,100 tens. If the question had said how many thousands are in 31,000, then we go to the thousands place and it'd be 31. And so hopefully that makes sense. If not, you can let me know. The idea here of how many hundreds are in 31,000, we're looking at the number of hundreds that there would be. And there'd be 310 hundreds in that number. There's a manipulative when working with base 10. They're called base 10 blocks, and I don't know if you'll run across these or not when you're teaching, but you might. And just in case you do, I want to make sure you're aware of them. What you'll see for these base 10 blocks is you'll have a little one that's a cube, and that represents a 1. And then you'll have sort of a long, skinny one like this, it's actually sectioned off to be 10 cubes, and that one's called a long. And then if we want to do the next place value, we're going to have 100. And so this one is also sectioned off so that it is 100. Mine's not going to have 100, but so that it is 100. And that's called a flat. And this gives students a way to sort of explore not only place value, but working with numbers, getting the different relationship between these, because we can see that 1 cube fits in one little spot here, and we can see that 1 long fits on 1 column here. They're pretty useful manipulative that you might see at some point. They're called base 10 blocks, and there's cubes, longs, and flats, and they represent ones, tens, and hundreds. I just want you to be aware of those. They come up in the book in a couple of the investigations, but basically, in case you run across those at some point, it's good that you've at least seen them. Now let's talk about clock arithmetic. So there's an example of a clock, and my question to you is this. If it's 10 a.m. now, what time will it be in 4 hours? And y'all can just type it in. I won't do a poll or anything like that. Two p.m., 2 p.m., 2. Very good. All right, we're all convinced on the 2. That's excellent. And you're right. If it's 10 a.m. now and I go 1, 2, 3, 4 hours, it'll be 2 o'clock. That is correct. And so let me get this straight. What you just told me is that 10 plus 4 equals 2. That's weird. But sure enough, When we're working in a base 12 system on this clock right here, when we're doing clock arithmetic, we can't have anything bigger than 12. We can't have 14. So 10 plus 4 can't be 14. Instead, 10 plus 4 is 2 because we're restricted by the system that we're in. And when we're on a 12 clock, that's what we'll call this. We'll call it a 12 clock because it has 12 numbers. 10 plus 4, sure enough, is 2. Let me ask you another one. How about 11 plus 6? What would 11 plus 6 be on a 12 clock? There are a couple of different ways you can get this answer, and I'm going to be curious to see what you tell me. Okay, we've got 5s all around. That's really good. One way to do this, obviously, is to say, well, it's 11 o'clock now, and I'm going to go 1, 2, 3, 4, 5, 6, and end up at 5 o'clock. And that's absolutely correct. Did anybody do it differently? Did anybody do it besides using the picture? Okay, well, let me talk through this a little bit here and give you an alternative. Nothing wrong with the picture. The picture is terrific. So if you like that and it works for you, that's good. And this is the type of question you'll see on the worksheet for sure. What's 11 plus 6 on a 12 clock? One thing you could do is, if I did 11 plus 6, I'd end up at 17. But I can't have 17 on a 12 clock. So what I could do then instead is I could say, well, okay, I'm at 17, but there is no 17 on a 12 clock, so that can't be my answer. One entire revolution around the clock is 12. Yes, very good, Nicole. Outstanding. Very good. You knew where I was going. One entire revolution around this clock is 12. So if I'm, I go around to 17, but I can't have 17. What I need to do is, instead of going an entire revolution around, I'm just going to subtract one of those revolutions. I'm going to subtract an entire revolution. I'm going to subtract 12 because that's one entire revolution around the clock. So I'll subtract 12, and sure enough, I'll end up at 5. All right, let's try one more of these before I do a poll with you. This one is going to be on a 12 clock. What is 3 minus 5? A way we might phrase that in language would be, if it's 3 o'clock now, what time was it 5 hours ago? But 3 minus 5 on a 12 clock. I won't do a poll for this. You can come up with that answer however you want to. We'll do some polls here in just a minute. So 3 minus 5 on a 12 clock. I've got a couple 10s. I'm getting consistent 10s. That's very good. I'm hoping everybody likes that 10. A couple different ways you can go. You can start at 3 and you can say 1, 2, 3, 4, 5 puts me here at 10 o'clock. So 3 minus 5 on a 12 clock, sure enough, is 10. Anybody do it the other way? 3 minus 5 and see what that gives you. So if I do 3 minus 5, yes, negative 2. Very good, Nicole. Now, negative 2 is not on my clock. What am I going to need to do to get me an answer that is on my clock? Because the answer I come up with here has to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It has to be one of those numbers. It can't be anything else. You guys really like that subtraction idea from over here. And that works here, but let's think about this for a minute. If I'm here at negative 2, to get to the same place, I want to go forward one full revolution. There you go. I like that one, Leslie. I want to go forward one full revolution because that's going to land me in the same place on the clock. The subtraction makes me nervous. If our number is too big for the clock, subtraction makes sense. If our number is too small for the clock, then we should add to go forward till we get to a number that is on our clock. So the subtraction works if our number is too big. If our number is too small, we'll add. And we're either going to add or subtract a full revolution to go around the clock. Very good, very good. All right, let's try a few of these. And we're just going to do a few for practice. We're going to do some polls and see how they go. My instinct is these are going to go great. Students tend to really like clock arithmetic, and I hope that's true for all of you. So 7 plus 6 on an 8 clock. Whoa, wait a minute, 8 clock? What the heck is this 8 clock stuff? Well, an 8 clock is, instead of going 1 through 12, it's going to go 1, 2, 3, 4, 5, 6, 7, 8. So it's a clock that only has 8 hours on it. And we're going to do 7 plus 6 on an 8 clock. I lied, we weren't ready for a poll yet. I was going to do this one, but I bet you're ready. But I'll let you tell me, just typing it in, what 7 plus 6 on an 8 clock is. We've got 5s, very good, excellent, very good. Let's see where we're at then. If we start here at 7 and I go plus 6, so I go 1, 2, 3, 4, 5, 6, sure enough, I end up at 5. So I agree with you, 7 plus 6 on an 8 clock is 5. If we did it the other way, okay, well 7 plus 6 would be 13, but I can't have 13 on an 8 clock. 8 clock only goes up to 8. So what I'm going to have to do is I'm going to have to make that number smaller. An entire revolution around would be 8, so I'm going to subtract 8, and sure enough, I'll end up in the same place. So you can either do this by looking at the picture, or you can do it by subtracting a full revolution because our number was too big. Okay, now let's try some polls. 6 plus 5 on that 8 clock. I'm thinking you were probably ready for that 8 clock poll, but it's okay. We'll do it now. Like I said, students tend to really like clock arithmetic, and I hope that's true for everybody. I think it's a really fun way to introduce other bases, because you'll notice we get an answer here that's not necessarily what we would get if we were base 10. Also, a clock is something we're all pretty familiar with. The idea that 10 plus 4 equals 2, we don't really think about it being in a different base, but it kind of is. So 6 plus 5 on an 8 clock. You can draw a picture, but you don't have to. We'll go another 10 seconds and then talk about it. Okay, outstanding. Very good. That's where I hoped we would be, and sure enough we are. 6 plus 5 on our 8 clock then. We could draw a picture of an 8 clock. And let's see, I want to start out at 6, and I want to go 5 from there. 1, 2, 3, 4, 5. Puts me over here at 3. And so 6 plus 5 is equal to 3 on this 8 clock. Another way to do that, 6 plus 5 is 11. I can't have 11 on an 8 clock. It only goes up to 8. So what I have to do is subtract in a complete revolution. I'll subtract 8, and that'll also land me at 3. We'll try a couple more of these, even though I'm feeling pretty confident. We've got time to do some practice. 4 minus 7 on an 8 clock. We'll go 10 more seconds and talk about it. Not unanimous, but very close. Okay, let's go take a look at this and make sure we're all together on it. A couple of different ways you could draw. You could certainly draw your 8 clock. And we want to go from 4, we want to subtract 7. So we'll start at 4 and we'll take away 7. We'll go to the left. 1, 2, 3, 4, 5, 6, 7. Sure enough, that gives us 5 as our answer. The other way to do this is to do 4 minus 7. That'll give you negative 11. The problem is our 8 clock over here, it doesn't have any negative numbers on it at all. So we're at negative 11. We can't have that as an answer. So we'll have to add an entire revolution. I'm going to have to add 8. And when I add 8 to that, that gives me negative 3. Well, that's no good. I'm not there yet. Even though I did a whole revolution forward, I'm still not to a number that's actually on an 8 clock. So I need to add another entire revolution. Negative 3 plus 8, that'll give me 5. Now I have a number that is on that 8 clock, so I have the right answer of 5. Please let me know if you have questions. That time we had to add 2 whole revolutions to get to a number that was actually on the clock. One more with an 8 clock. 5 times 4 on an 8 clock. We haven't done any multiplication yet, but I have a sense that you'll handle this one just fine. Just make sure your answer is something that is actually on the 8 clock. We'll go another 20 seconds and then talk about this one. Let's see what we've got. Okay, we're spread around a little bit more on this one. Let's be patient and careful as we go through it. Okay. So if you were going to do this one with a physical clock, you would still draw an 8 clock. And what you would do is 5 times 4. So you would do 5 times 4, right? So we'd go 1, 2, 3, 4, 5. That's 5 times 1. And then 1, 2, 3, 4, 5. That's 5 times 2. 1, 2, 3, 4. Oops. 1, 2, 3, 4, 5. That's 5 times 3. And 1, 2, 3, 4, 5. That's 5 times 4. It landed us on 4. So 4 would be our answer here. That's probably not the way most of you did it, but you could do 5 times 4. Do 5 4 times and see where you end up. 5 hours, 5 more hours, 5 more hours, 5 more hours. The other approach is to go ahead and multiply those. 5 times 4. And when you do that, you get 20. All right, so we're sitting with 20, and that would be great, except 20 is not on an 8 clock. So what I'm going to need to do then to figure out where 20 would be is I'm going to have to subtract an entire revolution around the clock. 20 minus 8. When I do that, that puts me at 12. That's not bad, but the problem is there's no 12 on my 8 clock. So I still don't have an answer that's on my 8 clock. So what I'm going to need to do then is I'm going to need to subtract another full revolution. I'm going to have to subtract 8 more. And when I do that, I end up at 4, which is a number that's on my 8 clock, and that's my answer here. So essentially what we had to do there is we had to subtract a revolution, still not on my clock, subtract another revolution. Now we have a number that is on the clock, so that's our answer. Are there any questions about that before we try something similar that is just a little bit different? Oh, tell me what you did, Stephanie. Let's talk about that. I think that's great. Twice and it was 6. Oh, okay. Yes, I like that very much. Okay. So not necessarily under 8, Leslie, but 8 or less, right? Because 8 could be the right answer. So 8 or less, that's correct. Now, I really like what Stephanie did there. Let's talk about that for a minute. Looking at what Stephanie did was, okay, well, let's see. 5 times 4. I know that's going to be 20. So as I count around this thing, instead of doing 5 plus 5 plus 5 plus 5, I'm going to go, well, there's 8. There's another 8. That's 16. 17, 18, 19, 20. Excellent. Outstanding. I think that is terrific. Knowing you were going to 20, that was a way to get there. All right, let's try one that's like this, but similar. It's very much like the multiplication. I do want to change the number here from 33 to 21. And I do want to do a poll here. Find the equivalent of 21 on an 8 clock. Now, this isn't that different from what we just did with multiplication. Essentially, if you're at 21, on an 8 clock, where would you be? I'll do a poll for this one. So if you were at 21, where would you be? We've done all this work on an 8 clock, but keep in mind, your clock could have any numbers. It could be a 6 clock, it could be a 4 clock, it could be a 9 clock. None of those things really matter. What happens is the process is the same, no matter how many numbers are on the clock. Let's go ahead and take a look at this one. Not quite unanimous, but definitely strong agreement. As we talk through these, if you see something that you want to ask about, please don't hesitate. So 21 on an 8 clock. And there's a couple of different ways you could do this. You could certainly make an 8 clock and count it. Kind of the way Stephanie did last time. There's 8, 16, 17, 18, 19, 20, 21. So our answer is going to be 5 here. The other approach is to say, well, if I'm at 21, that's not on the clock. So in order to get a number that is on the clock, I need to subtract 8. And what that does is that puts me at, let's see, 21 minus 8 is 13. 13 is a great number, but it's not on an 8 clock. So one thing I'm going to have to do is subtract 8 from that also. And then that's going to put me at 5. Something that just occurred to me is we've been doing so many 8s, and I said it out loud that the clock doesn't necessarily have to have 8. I want to just kind of change it up a little bit and try one more with you here. How about you do this one? Five plus 9 on a 7 clock. Just to make sure that we're aware that there are other clocks out there, 5 plus 9 on a 7 clock. And I don't have a poll for this one, so when you have it, you can just sort of type it in for us. 5 plus 9 on a 7 clock. All right, 7's right down the line. Well, let's see what we've got here. If you wanted to draw your clock, you could do that. And you'd have a 7 clock this time. So it's going to have a 7 at the top. 1, 2, 3, 4, 5, 6. It doesn't have to be perfect. We're just using it to kind of keep track of where we are. And if I were to do 5 plus 9, so I'm starting here at 5, and I need to add 9 to that. 1, 2, 3, 4, 5, 6, 7, 8, 9. Sure enough, I ended up at 7. Feels a little weird that the answer is 7, but that's okay. A 7 clock has the numbers 1 through 7 on it, so totally fine. The other way, 5 plus 9 would be 14, but 14 is not on a 7 clock, so I need to subtract an entire revolution. So I need to subtract 7, which gives me 7. 7 is on my clock, and so I'm good with that as an answer. Let me know if there's anything in there that doesn't make sense, and that this can happen with any number of clock. If we need to add or subtract an entire revolution, keep in mind that that's going to be based on the size of the clock that we have, whether it's a 12 or an 8 or a 7 or anything else. Oops. All right. That's clock arithmetic. Now let's talk about modular arithmetic. The great news about modular arithmetic, if you liked clock arithmetic so far, the great news about modular arithmetic is that it is almost exactly the same. There's just one major difference. What you'll notice when we look at a clock, 1 through 12, 1 through 7, 1 through 8, there isn't a 0. In modular arithmetic, we do have a 0. So we will have zeros in modular arithmetic. We didn't have them in clock arithmetic. We do have them in modular arithmetic. And so just to sort of make a little bit of sense out of the idea of modular arithmetic then, let's say we're talking about a mod 5 system. this system's going to have 5 digits in it. But it's not going to be 1 through 5 like a clock would be. Instead, the mod 5 system would be made up of 0, 1, 2, 3, and 4. There's not going to be a 5 in the mod 5 system. And if you're thinking, well, why would you call it mod 5 if there's no 5? That's reasonable. We call it mod 5 because it has 5 digits, 0, 1, 2, 3, and 4. I want to link this to the base 10 system that we work in all the time. Our base 10 system. It has 10 digits, and those are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Notice, the largest digit in a base 10 system is 9. The largest digit in a mod 5 system is 4. So there's definitely parallels here between what we do with modular arithmetic and what we do in our base 10 system. Everything else in modular arithmetic is going to be just like it was in clock arithmetic, except keep in mind that if it's mod 5, our numbers only go up to 4. Let's look at a problem that involves mod 5. Oh, and if you want to draw a picture of a mod 5 system, you just have 0, 1, 2, 3, 4. Because you can absolutely do these on a picture the same way you did the clock arithmetic on a picture. Okay, let's take a look at one. 3 plus 4, mod 5. I'm going to make a poll for these. So this is mod 5, and we're doing 3 plus 4. You can do this with a picture, or you can do it computationally, whichever way you're comfortable. If our numbers get big, the picture might not be as fast, but it still works. It still works. We'll go another 15 seconds and then talk about it. Not quite unanimous, but strong agreement. That's really good. If you have any questions, please don't hesitate to ask them. We're going to talk through this. And if you see something that you're not sure about, don't hesitate to ask. So we have 3 plus 4, mod 5. As soon as we see mod 5, we know a couple of things. We know that the only possible answers here are these. That's it. Anything else can't be our answer, because that's the only numbers that exist in a mod 5 system. And if you want to do it with a picture, you certainly can. And you could say, well, okay, 3 plus 4 would be, I'm here at 3 and I need to add 4. So I go 1, 2, 3, 4. I end up at 2. So the answer's got to be 2. You don't have to use a picture, though. Instead, you could do 3 plus 4. Well, 3 plus 4, I know that's 7. The reason that can't be our answer here, though, is because in the mod 5 system, these are the only possible digits. That's it. Those are the only numbers I get. 0, 1, 2, 3, 4. So what I need to do then is I need to subtract. I need to go backwards a complete revolution. Now, 0, 1, 2, 3, 4. What is a complete revolution here? Well, it's 5 numbers because it's mod 5. So we'll subtract 5 from that and end up at 2, which is the same answer we got by drawing the picture. there are 5 numbers as I go all the way around. So if I subtract a complete revolution, I do need to subtract 5. Try another one. 5 minus 7, mod 9. Again, I'm going to set up polls for these. So far, the polls have been fantastic. So that's great news. I'm optimistic that you're really going to like clock and modular arithmetic. I think they're really fun, and I hope you do too. That's true of a lot of topics that we cover for me, I guess, and I hope it's true for you. This is one that I really like, and it really sets us up to do well with the rest of section 2.1 when we start working in other bases. But for right now, we're just talking about clock and modular arithmetic, addition, subtraction, multiplication. What is the equivalent of type of questions? We'll go another 10 seconds and talk this through. All right, outstanding. Okay, so 5 minus 7 mod 9. As always, there's more than one way to do this. We can draw a picture here. We'll have 0, 1, 2, 3, 4, 5, 6, 7, 8 is the biggest number in a mod 9 system. So I would just have those 8. Certainly not a work of art, but it can work to help me do the counting here. If I start out at 5 and I go to the left 7, I got to go backwards 7. That's 1, 2, 3, 4, 5, 6, 7. I've ended up at 7. So by drawing the picture, I can see 7 is going to be my answer. Let's see how we get there. If I were to just do 5 minus 7, that would give me negative 2. And that's great, except that's not on my mod 9 system. I don't have a negative number in the mod 9 system. So what I need to do is I need to add an entire revolution, add all the way around, Negative 2 plus 9 puts me at 7. That is in the mod 9 system, so that's my answer. I get a sense that you're doing fantastic. We'll just do a couple more of these. But I really like how well this is going so far. 4 times 3, mod 6. I'll do a poll for this one too. We'll go another 15 seconds and then do this one together. Okay, we're spread around a little on this one. Got quite a few 6s in there. So let's take a look at this one. 4 times 3 mod 6. All right, so if I were to do this by drawing it out, I could have a mod 6 system. And I have to remember what mod 6 means. Mod 6 means that I have 0, 1, 2, 3, 4, and 5. That's it. Those are the only numbers in this system. That's it. So let's see, 0, 1, 2, 3, 4, 5. So there's my mod 6 system. I only have those numbers. Those are the only possibilities. If I have 4 times 3, so I could do 4 3 times. Let's see, there's 1, 2, 3, 4 times 1, 1, 2, 3, 4 times 2, 1, 2, 3, 4 times 3. I ended up at 0. So 0 should be my answer here. It's okay to have 0 as an answer in a mod problem. In a clock problem, we never have 0 as an answer because we don't have 0 on a clock. But in a mod problem, 0 is okay. And here, 4 times 3 would be 12. But I don't have a 12 in this system. So I need to subtract 6. I need to go all the way around this thing backwards. Oops. I need to go all the way around this thing backwards 1 time. That puts me at 6. And kind of feels like, well, it's mod 6. It ought to have a 6. Well, it doesn't. Because mod 6 does have a 0, and because there's only 6 digits allowed, 0, 1, 2, 3, 4, and 5 are the only choices in a mod 6 system. So I don't have a number that's in my system yet, so it can't be the answer. So I need to subtract 6 again, and when I do that, that's when I land on a number that is in my mod 6 system, and so that's my answer here. Let's try one more. Find the equivalent of 29 mod 5. There are a couple different ways you can go here on this one. So we may talk about this one a few different ways after you have it. I'll give you a little time on this one. It's kind of like the multiplication problems. I'll give you a little time on this, and then we'll talk about a couple of different ways you might go to get the answer here. I'll see what you've done, honestly. So you can do this one by drawing a picture. Stephanie had a great approach for that, and that's actually something I want to talk about when we go through this. And then there's also approaching it like a multiplication problem, but knowing you need to have an answer that's in the mod 5 system. We'll go another 15 seconds and then talk about this one. Okay, not unanimous, but strong agreement. It's kind of where we've been for a lot of them today. A lot of them have been unanimous, which is really good. We've done terrific with this concept. At least that's the perception I have, but I'll give you a chance to ask questions here in a few minutes. So here we have the equivalent of 29 mod 5. We've always started by drawing a picture, so let's do this one a different way. So I'm here at 29 mod 5, and I know the mod 5 system is only 0, 1, 2, 3, and 4. So my answer has to be one of those. Can't be anything else. And 29, certainly not going to get that done. So what I'll need to do is I'll need to subtract an entire revolution around. I'm going to subtract 5. And what that does for me is that would put me at 24. Still not in the mod 5 system. So I guess what I'll do is subtract 5 again, see where that gets me. That gets me to 19. Okay, this might be a long road, but I'm just going to keep walking it. I'm going to subtract 5 again, and that'll put me at 14. Still not in the mod 5 system. I'll subtract 5 again. I'm getting there. That puts me at 9. Ooh, I'm close. And then let's see. One more time, I'll subtract 5 again, and that puts me at 4. Finally, I got to a number that's in the mod 5 system, and I have an answer of 4. I want to talk about Stephanie's approach, and then I want to open it up to see what you might have done differently than either of those. So it's mod 5 system, so it's 0, 1, 2, 3, and 4. And what Stephanie would do, I'm guessing, maybe not, is, all right, well, that's 5, 10, 15, 20, 25, 26, 27, 28, 29. We land at 4. That's outstanding. Did anybody do something different from those two approaches? Outstanding, Courtney. Tell me what you divided. I love it. Everything you've typed there is perfect. So 29 divided by 5 equals 5 point something. And we're not that interested in the remainder. This is kind of like those questions like the hip hip hooray question that we had back in chapter 1, where what I really care about is the remainder, not the decimal part of the remainder, but what is the remainder? And so what Courtney did here is perfect. It's excellent. The other two approaches are great. If you like those, you can do those. But what Courtney's done here is outstanding. So if I do 29 divided by 5, I get 5 point something. And what that tells me is the same thing I saw using the approach that I'm giving Stephanie credit for, is we're going to make 5 complete revolutions around this thing. And when I do those 5 complete revolutions around this thing, at that point, I've done 5 times 5. I've made it to 25. And exactly what Courtney said there, 29 minus 25, I still have 4 to go. And I'll do that by going 1, 2, 3, 4, and land at 4. And so there are 3 different approaches you can take to answer a question like this one. You can start at 29 and just subtract 5 until you get to a number that's actually allowed to be an answer. You can draw the picture and just count up until you get to 29. Or you can use this approach that Courtney did here and divide. Be careful. The decimal part of the remainder is not important to us. What's important to us is how many full revolutions do we make, and how much of the 29 does that count for? And then once I know that's counted for 25, I have 4 more to go. I'll just count those. 1, 2, 3, 4 puts me at 4 for an answer. Any one of those approaches will get you to the same answer, that is 4. The equivalent of 29 in